Okay, so what we're doing today is this warm-up where we're given a piecewise function and we graph it. And then our lesson after that, we're doing the opposite. We're going to be given the graphs and we're going to determine the equations for ourselves. And this is the last new material for the week. Tomorrow is just a practice day, and then Friday we have a quiz. Okay. So our two pieces here are, one is, what's the parent function for this first piece? Absolute value. So if you're still struggling with your parent functions and how to transform them, you're just getting more behind and more behind every day. So I know we tested on it, but we're still using those skills this week. So try to get that stuff down as fast as possible. It's not that you can't just sit there with your parent library booklet and spend the time slowly going through each thing. You absolutely could and be successful. But you aren't doing that, and so not only does it make you take longer, but then you can't go forward with the next thing because you don't have the fundamentals down. So please be sure to do that. It will make your life easier and you'll feel less frustrated. So this first one, that parent function is absolute value, and the transformations are what? So inside is -1, so that means it's going to go which way? So it's going to go right 1 and then down 5. So the parent function is going right 1, down 5. Remember, absolute value looks like it's the V, okay, and the vertex is originally at 0, 0. So I'm going to take that vertex and just go right 1, down 5. There's no stretch or anything, which means there's no A value. So I can just pretend like this is my new 0, 0, and I'm just going to fill in some points. I'm going to fill in 1, 1, 2, 2. And I'm just going to sort of fill in stuff, and then I'll take a break in a minute and try and figure out which domain I need this on. Okay. So I'm filling in the basic form. I recommend you use pencils because you're going to be doing lots of erasing or correcting or trying to figure stuff out. So this is my basic form. I only need it for all x's that are, what does this sign mean? Do I need less than 3 or bigger than? Less than, right? It's always pointing to the smaller thing and opening to the bigger value. So I need to keep that graph for everything where x is less than 3. So I'm going to erase some stuff. So I'm going to find where x equals 3 on my graph and erase anything that comes after that and keep everything that comes before. And then I have to ask myself, before I even fill it in, right here where x equals 3, can I keep that as a closed circle, or does it need to be an open circle? Open, right? Because there's no equal bar right there. Okay, there's not an equal bar there. So we know we need an open circle. So I can erase this and give myself an open circle. So as you work through these problems, it's completely fine, bless you, to put in stuff as you need it, erase it when you no longer need it, anything that helps you see what needs to be done. And I'm going to connect the dots there, blah, 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 blah. Okay. So there's that piece. Absolute value, right 1, down 5, everything less than 3. This next piece is linear. And I recommend just don't necessarily think about that as a transformation. You're welcome to. But I recommend thinking about it as an mx plus b simply because we have done that a million times. We can do that in our sleep. Which piece tells me the y-intercept? The b, right? So the y-intercept is 7. The slope is -2, which means -2 over 1. That's your rise over run. So we start at point that's 7. See, I'm not even thinking necessarily about where I need to cut off the domain. You're welcome to, but it might be easier for you to just get the basic form down, then think about where you're cutting off the domain. So there's 7. My slope is down 2, right 1. So I'll just do that for a while. Stop when I kind of feel like maybe that's enough. I can always add more points in if I need to. So that green stuff is the basic form. I need to keep everything that is what compared to 3? What's opening to x? 3 is the smallest value, so I need everything bigger than 3. Which means I'm erasing everything that's less than 3. So here's where x equals 3. I want to erase everything that's smaller than 3. I don't need that anymore. And then I have to figure out at 3, can I keep that a closed circle or do I need to make it an open circle? Yes, it can stay closed because it's got an equal bar. And it's going to infinity. And that is my 2 pieces. I should say those are my 2 pieces. Excuse me. But I still need to do domain and range. So domain is the x values. It kind of looks, and so when you're finding this domain, okay, it's asking for the domain of the entire function. It's one big function made up of 2 pieces. And so it seems kind of like, because there's arrowheads in both directions, it seems kind of like it could be negative infinity to positive infinity. But, excuse me, we have to check out the special circumstances. And so right here where this open circle is, I have to inspect it a little bit. I'm looking at, so right here, that x value at 3 has no point here, but there is a point there at x equals 3. So as long as there's some point anywhere at x equals 3, then there's no break in your domain. Okay? How would this have changed in order for there to be a break in the domain? If this was what kind of circle? Open, right? Because then there would have been no point anywhere at x equals 3. But right here for x equals 3, we have a point. And then going to the right, all those x's have points as well. Bless you. So the domain is negative infinity to positive. And then the range is bottom to top. It kind of looks like negative infinity to positive because of the arrows. But again, we have to check this special circumstance. And now we're looking at y values here. So here's this open circle. So there's no y value there. But if I go this way or this way, there are y values on the other parts. So that means there's no break in the y's either. So the y values go negative infinity to positive as well. As long as there's some y value somewhere along that line, it's good. And then we have the second piecewise function. That first one is the parent function that's quadratic. What's its transformation for the x squared? Just down 1, right? It didn't go left or right at all. So it's 0, 0. There's no stretch or compression there because there's no a value. So I can just start filling in my parent points like this. 1, 1, 2, 4. And now I've got some points there. So now I'll look at the domain restriction and see if I need to either add points or which ones I have to erase. So for this transform function, I need all the x values that are less than negative 1. So to the left of negative 1. So I find where negative 1 is. It's right here. I'm keeping everything to the left. So I'm erasing everything to the right. So that's gone. Do I keep this boundary point as solid, or does it need to be open? Open, because it's all values less than negative 1, not equal to. So I use my eraser. I erase that point, and I make it an open circle. And then I draw it in like that. And the next part is linear, negative x plus 4. I like to do mx plus b, which means my y-intercept is 4. My slope is negative 1 over 1. So I'm going to go down 1 to the right one. So I'll plot the 4 first. Down 1, so down 1, right 1. Do that for a bit. Blah, blah, blah. So I'm going down 1, right 1, down 1, right 1. Now I stop to look at my domain. It says I need all x's greater than negative 1. Well, so far I've only plotted at x equals 0. I don't have a point yet where x is negative 1. Remember, your slope can go the opposite direction as well. Instead of down 1 over 1, it could have been like this. Up 1, left 1. So I'll do that. I'm going to go up 1, left 1. Now I have a point for -1, which was my domain cutoff. Can I keep it a closed circle, or do I need to change that point to an open circle? Open, right? Because there's no equal right there at the -1, so I go erase it. And then I connect all that. Oh, so then we talk about the domain range. There is a break in this domain. Okay? So you're going from left to right. The only actual point of interest you need to look at is right here, where the open circles are. But on this x value, there are no solid points anywhere. There's no solid dots, and there's no lines that are solid going through there. So that is where the break in the domain happens. There's nothing defined. So when you go to write your domain, it's -infinity to -1. With a parenthesis, it breaks and continues again after -1. And we join those with a U. They're not brackets, that's right. And then the range, the y values look like it goes from -infinity to positive, but we want to look at those open circles again and just be sure that if there are any y values there. So now we're looking here at this open circle, at its y value, but on this other piece, it's got a y value there. Okay, so that y value is good, it's covered. And then we come up and look at this y value where the other open circle is, but there's a point here at that y value. So if there's a point elsewhere, that y value is covered. So there's actually no break in the y's. So this is -infinity to positive. Okay, did anybody get all of that correct? Absolutely every small little thing? Okay, very good. So you have two practice problems there. We're going to determine the equation of the piecewise functions, including the domain for each piece. Please also, so what we're doing is starting with a graph, and we're ending up with something that looks like this. We're coming up with this part on our own. Please notice that we've been working with interval notation, but piecewise functions are traditionally written, the domain pieces are written with inequality notation. So if you're unsure about which way to point arrows and stuff like that, I'll talk about some of that as we go through. Always remember it opens to the bigger thing like a mouth would because it's hungry, and points to the smaller thing because it's very judgmental and telling it is bad because it's smaller. All right, so here we go. How many pieces do you see on this function? 2. All right, so let's just talk about a few things here. For that first piece, what's its general form? Or like, what would you think that is? Y equals mx plus b. Some people want to say it's absolute value. You could try an absolute value here, but in my opinion, it sort of just makes it harder than it has to be. So I would do mx plus b there, and then that second piece, the curved piece, it's what kind of parent function? The curved one. Quadratic, right? And so we're going to have to figure out how the x squared was transformed, or was there a reflection, was there an a value? So these are all things we're going to have to figure out. Other stuff we're going to talk about is when you're looking at the first piece, that line, notice it has a left and right boundary, right? Like, what's its left boundary for the line? -2, and it stops at 1. We'll use that information. The quadratic starts at 1 and keeps going on and on to infinity. So we're going to use all those things to try and come up with the equations. Now, when we do the equations for x squared or absolute value, on your test that we just took, the very last question on that test was to come up with an equation and to find a. And I circled some people's problems if they just gave me the answer because they just read it off the graph, because that was a skill we were learning. We were learning the algebra, and I was testing you on that. Now, I've already tested you on that, so you can just eyeball it now, okay, on the graph. Okay? I'm not going to ask you to do the algebra to come up with the A, because that moment's passed. And I want it to be faster and easier for you. So here we go. I'm going to approach this by just giving myself a bunch of notes in the margin, stuff I'm figuring out, and then at the end I'll put it all together in the proper notation. So here's how that's going to go. I'm going to look at this piece first. I'm going to say, all right, I got this piece. I know it's going to be a line, and that this is the general form for that. The B stands for the y-intercept. What is the y-intercept? -1. So I just plug that in for B. And to figure out the slope, which is the only other part that you need, you just pick 2 pretty points off there. You figure out your rise over your run. And everyone can pick 2 different points. As long as you're simplifying it, you'll get the same answer. Like, so for example, you might go up to over 1. I might decide I like this point. So I might go up here. That's 1, 2, 3, 4. And to the right one, that's +2. But we both end up with the same answer, because when I go to do my slope, I'd say that's 4 over 2. And then I would simplify that. Okay, 2x minus 1. So you'll get to the same answer. Just if your work looks different from your partner's, if you're trying to work together like tomorrow, for example, don't worry too much about it. You're probably on the right track. And just real quickly, I'm going to throw down the domain and interval notation. I'll figure out the inequality later. This is from -2 included to 1 included. So I'm just going to make a note about that. Okay, and I'll write it as an inequality in a bit when I'm trying to be all like formal and stuff. So that's the first piece. The second piece is quadratic. And here's the general formula for that. A times x minus h squared plus k, or x minus h quantity squared. So here are the things we have to figure out. We've got to figure out the vertex and the A value. Remember that the A value represents a stretch or compression and a reflection. Let's do the vertex first because it's easiest. What is the vertex for that piece? 3, 5. Okay, it's right here. That's my h and my k. So those just get to be plugged in. 3 for h, 5 for k. Because the quadratic is reflected down, I know what about the A value. It's negative. And so now we figure out what the number part of the A value is. So I'm going to just assume that there is no stretch or compression. I'm going to assume that to begin with. If that is the case, then I can go over 1, down 1, and hit a point. Did I do that? Yes, right? Because that's a parent point. The parent points haven't changed. It's 1, 1, just reflected. So I know that the A value didn't change at all. Okay, it's still a value of 1. So my final answer here is negative x minus 3 squared plus 5. And the domain is from 1 excluded to infinity. All right, so I did a lot of good math here, but I'm not done. Okay, the instructions said to write it as one single piecewise function. Right now I just have a bunch of information. So now we're going to put it all together. It's going to look like this. F of x equals curly braces, squiggly wigglies. Y equals 2x minus 1. What am I dropping off of there before I write it down? What am I going to drop off? The y equals, right? So I'm just going to have the 2x minus 1 because that's the function part. And the domain is from -2 to -1. We're writing it as inequalities now. So what I'm trying to write is all x's that are between -2 and -1. So all x's between -2 and 1. It should be positive 1, right? Yeah, okay. And I have the equal bars because of the solid dots on the boundaries. And then I have my second function piece. From 1 to infinity. There are 2 main ways people like to handle inequalities when the infinity is involved. Here's my way. I would write all x greater than 1. That's how I like it. You can also do this. All x is between 1 and infinity. This is also correct. Okay, I'll take either form that you like. Okay, because this still is saying that x is greater than 1. See here, it's pointing to the 1. Here, it's also pointing to the 1 because the 1 is smaller. But this might seem more intuitive to you when you're comparing it to the interval notation. Okay. So you try that second problem for a few minutes, okay? So how many pieces we got? 3. That farthest left piece, that's just a horizontal line. It's kind of funky, right? We're not used to seeing that, but it's easier than it seems. That's the line where y equals 5 everywhere. So how do you write that as an equation? Y equals 5. And then its domain piece is from negative infinity to negative 2. Is that negative 2 included? Yes. Okay. So that's this blue part right here. We did that. The red part is a line. And here's why I recommend not thinking of this as a transformation of the identity, because the y equals x, there's no vertex or initial point or inflection point to identify where it's beginning. So it's hard to think of it as a transformation, like did it go to the left 2 or the right 4 or what did it do? Because there's no identifying point to help us out. So that's why I recommend not thinking of the identity function as a transformation and just going straight to your mx plus b. And so in this case, b is what? 1, right? So there's my y-intercept, so that's plus 1. And then I just need to figure out the slope. So let's say I went down 1, right 1. So down would be a negative 1, right 1 would be a positive 1, and that's just negative 1. Maybe you did a point where it was 2 and 2. It still simplifies to negative 1. And then what's its left boundary and right boundary? Negative 2 excluded to positive 2 included. And we'll figure out that as an inequality here in a bit. And then this last part is a quadratic. So here's our general form. The vertex is 2, negative 1. So 2 goes in for h, negative 1 for k. And we have to figure out what the stretch or compression is. By the way, is A going to be negative? No, because it's not reflected down. So at least we know that part. Here's how to determine what the stretch or compression is. From the parent function, so this is my shifted vertex. If there was no stretch or compression, I would expect to see a point at 1, 1 right here. Okay, but it's not there, right? Here's where the point actually is. It's over 1, up 2. So what does that mean happened to the y value? Stretched by times 2. Okay, so that means our a value is 2. So y equals 2 times x. And then you could also check if you wanted to do one more just for fun. Bless you. We would expect the second point to be over 2 and up 4, but it's actually over 2 and up 8. So that means the y was times 2 again. So here's your final answer. Oh, and that was from 2 excluded to infinity. So real quickly, so I know that your inequalities are good. By the way, you don't have to call it f of x. You call it any of the letters of the alphabet. So we had 5 from x less than or equal to negative 2. You could also write that as negative infinity. Oops, no commas, I don't know. Could also write it like that. The linear piece is negative x plus 1. Negative 2 excluded to 2 included. And then the quadratic piece, I would write that as all the x's greater than 2. You're also welcome to write it as all the x's between 2 and infinity. Okay. Any questions about that? Feel a little bit better?